Hi everyone, welcome to 10-Minute Physiology. In today's video, I will be describing to you what the resting potential is in hopefully under 10 minutes. So let's give it a go. So here we have our hypothetical cell, and our hypothetical cell has a plasma membrane that separates two compartments. The first is the intracellular fluid, or ICF, which is the fluid inside the cell, and the ICF, which is the fluid outside the cell, or otherwise known as the interstitial fluid. Now inside the cell, we have a certain concentration of potassium, and outside the cell, we also have a certain concentration of potassium. Now note that the concentration of potassium inside the cell is much greater than the potassium concentration outside the cell. We also have a certain concentration of sodium outside the cell, and a concentration of sodium inside the cell. And the concentration of sodium outside the cell is greater than the concentration of sodium inside the cell. Now in the plasma membrane, we have a potassium channel that when open allows potassium to flow through it. We also have a sodium channel that when open will allow sodium to flow through it. Now when the potassium channel is open, the potassium will flow down its electrochemical gradient from the inside of the cell to the outside of the cell. So when this channel is open, potassium flows out of the cell. And when the sodium channel is open, sodium will flow into the cell down its electrochemical gradient. Now inside the cell, we also have another transporter called the sodium-potassium pump, or the NKP. Now the NKP is a transporter that uses the hydrolysis of ATP in order to pump sodium outside of the cell and potassium into the cell. So it will pump 2 potassium into the cell and 3 sodium out of the cell. So what is the net result of this hypothetical cell? So the net result of this hypothetical cell is that we have 2 potassiums flowing out of the cell through the channel, and then 2 potassiums being transported into the cell by the NKP. So we have 2 potassiums flowing out, 2 potassiums being transported in. And at the same time, we also have 3 sodiums moving into the cell through the sodium channels, and 3 sodiums moving out of the cell via the NKP. So we have 3 sodiums moving out of the cell and 3 sodiums moving into the cell. So what is the net current in this hypothetical cell? To calculate the net current, we have to take the sum of the net potassium current moving through the cell and the net sodium current moving through the cell. So we can calculate each of these net currents by using this equation here. So for the net potassium current moving through the cell, we take the sum of the current of potassium moving outward and the current of potassium moving inward. And we do the same thing for sodium. Now it's important to realize that by definition, any current moving out of the cell is going to be positive, and any current moving into the cell is going to be negative current. So from this, we can calculate what the net current is, and when you do the math and the arithmetic, what you get is a net current of 0. Now note that we only get a net current of 0 only when the cell is at rest. So when the cell is at rest in the steady state, we have a net current of 0. And this is only true for when the cell is at rest. So now in order to define what the membrane potential is, or what the resting potential is, we need a better equation for current. And in order to derive that, we use V equals IR, or Ohm's law, and we solve for the current. So current will equal V over R. And we also know that the resistance is going to be the inverse of the conductance, where G is the conductance. So plugging this into the equation, we get I is equal to V, which is the voltage, times the conductance, which is G. So I is the current, V is the voltage, and G is the conductance. Now we are going to substitute a different factor for the voltage, and in this case we are using the driving force. And you can think of the driving force as the force being applied to an ion, which either moves it into or out of the cell. I have another video on the driving force in my channel as well. So if we substitute in the equation for the driving force, what we would get is that the current of an ion would be the membrane potential minus the equilibrium potential for that ion times the conductance. So now that we have an equation for the current moving through a cell, and we have an equation that can describe the current, we can now find what the resting potential is. Now, the resting potential, as we know, is going to be the membrane potential when the cell is at rest. And when the cell is at rest, the current, remember, is going to be zero. So the net current is zero. So therefore, the amount of current of sodium flowing into the cell should be equal to the amount of current of potassium moving out of the cell. And we will substitute in our equations for current for both potassium and sodium. And what we're going to do is some simple algebra in order to solve for Vm. And the equation that we get is the equation below. Now, inside this equation, what we have is, first of all, the delta Vm stands for the membrane potential. And the membrane potential is basically the voltage across the membrane. And what we see is that the membrane potential is going to be a function of the relative conductances of each ion and their equilibrium potential. So this term right here, the GK over the GM, and the GNA over the GM is going to be the relative conductances. And you can think of the relative conductance as how permeable the particular ion is to the cell relative to the total conductance of the cell. And the EK and ENA stands for the equilibrium potential of sodium and potassium. So what does this equation actually mean? So this equation is basically telling us that the membrane potential depends upon three things. The first thing is it depends upon what ions are present. So in our hypothetical cell, the membrane potential only depends upon sodium and potassium. However, in real cells, you also have chloride, bicarbonate, magnesium, and many other ions that are going to be present. But the key thing to take note of is that the membrane potential is going to depend upon what ions are present. The second thing that the membrane potential will depend upon is the equilibrium potential for each of these ions. And remember that the equilibrium potential can be calculated using the Nernst equation, and it basically takes into account the charge of the ion as well as the concentration of that ion inside and out of the cell. And the last factor that the membrane potential depends upon is the relative conductances of each ion. So what is the relative conductance? It's basically telling you how permeable that ion is to the cell membrane. So in other words, the more ion channels you have open, the higher the relative conductance and the greater the contribution that particular ion plays to the membrane potential. So you can think of this equation as a weighted average. The more conductive the cell membrane is to a particular ion, the greater the contribution it makes. And in fact, this is why the resting potential is closer to potassium than sodium. This is because at rest, the cell membrane has much more potassium channels open than sodium channels open, and this means that the relative conductance of potassium will be higher than sodium. So therefore, the resting potential is going to be much closer to the equilibrium potential of potassium than it is to sodium. So that's what the resting potential is. I hope this made sense to you, and I hope this clears some things up. I hope to see you next time for my next video. Thank you.